In this demo, we present the use case of remote control of a robotic dog for Industry 5.0. Let's see what this demo is about. We have a remote operator who uses a real-time digital twin to understand where the robot is. The robot is controlled through a set of gestures, allowing for easy operation. For better control, the robot also provides a real-time video feed. To meet the KPIs of this use case, deterministic flow management is essential for safe functioning. Low reliability, high jitter, or high latency could result in undesirable scenarios. Powered by the Predict 6G multi-domain data plane and the artificial intelligence control plane, we can achieve the required quality of service for this use case. The KPIs necessary for the correct functioning of the use case are 0% packet loss, 15 milliseconds end-to-end delay, and less than 1 millisecond of jitter. Our demo setup, built in the 5 Tonic Lab, is the result of the collaborative efforts of our partners, who work together to deploy both the data plane and the control plane. In this use case, the robot is connected to TSN enhanced Wi-Fi, which supports QBV, ATS, and PTP over the air. Next, we have a TSN Ethernet domain, composed of multiple industrial TSN switches performing frame replication for an extra layer of reliability and QBV for traffic scheduling. Finally, the 3GPP network is a commercial 5G network, enhanced with determinism by the Predict 6G features provided through the TSN translators. Now, let's dive into the core components of our demonstration. We'll begin by examining each TSN domain individually to get a clear overview of its unique capabilities. First up, we have our Wi-Fi TSN domain. This setup is powered by an Intel software stack and has been deployed in collaboration with UC3M. At its heart, this domain uses a straightforward yet powerful architecture consisting of a soft access point and a station. It brings deterministic networking to wireless environments by implementing time-aware shapers over Wi-Fi, leveraging the 802.1 QBV standard. This allows us to create precise deterministic transmission windows for time-sensitive data flows. A key feature is its ability to handle both real-time and best-effort traffic simultaneously. It achieves this through offset synchronized gating mechanisms, ensuring low latency and predictable performance, which is crucial in shared wireless environments. Next, let's turn our attention to the Ethernet TSN domain. For this, we are using state-of-the-art industrial switches from Relium. These switches are the backbone of our wired deterministic network and implement a comprehensive set of key TSN standards. In this demo, we are specifically leveraging 802.1 QBV for time-aware traffic scheduling, precision time protocol for microsecond-level time synchronization across all devices, and 802.1 CB, also known as frame replication and elimination for reliability, which provides seamless zero-packet loss redundancy for critical data streams. This combination of standards allows us to build a highly reliable, deterministic, and fine-grained communication link for our most critical applications. In the other side of the multi-domain networks, we can find a 5GSA commercial network, which it is enhanced with TSN and determinism support developed by Predict 6G project. For this demonstration, the 5G network will use urgent-based scheduling, based on IEEE 802.1 QCR-ATS, deterministic traffic classification, and de-jittering scheduler to stabilize the network performance indicators, especially for the one-way delay, which is able to provide jitter less than 1 millisecond, around 100 microseconds. In this next phase of our demonstration, we introduce our multi-domain data plane, built upon deterministic networking, or DetNet, routers. What we've developed is a fully open-source and programmable DetNet router that runs on Linux. It leverages powerful kernel-level technologies like XDP and eBPF to achieve high-performance packet processing, as illustrated in the architecture diagram. This allows us to efficiently separate high-priority deterministic traffic from best-effort data at the earliest possible stage. Crucially, the platform integrates IEEE 802.1 AS for time synchronization with DetNet's data plane functions, ensuring precise coordination across the network. The results speak for themselves. As you can see from the performance graphs, each node in the chain, whether for encapsulation, forwarding, or decapsulation, contributes around 100 microseconds of latency and maintains a jitter of less than 20 microseconds. This provides the stable, predictable performance required for multi-domain, critical applications. Now, let's explore how we achieve seamless, end-to-end deterministic connectivity across multiple distinct network domains. The key is our DetNet encapsulation strategy, which is based on MPLS. As the diagram shows, we create a single end-to-end tunnel that can span heterogeneous technologies like Wi-Fi TSN, Ethernet TSN, and even 5G networks. This encapsulation preserves the flow's identity and critical timing metadata across every segment of the journey. We use a technique called label stacking. This allows us to embed domain-specific scheduling context, such as time-aware shaping rules, VLAN headers for Q2BV, or redundancy information for FRER, directly into the packet. This is highly efficient, as it avoids the need for reclassification at every hop. Ultimately, this approach abstracts the complexity of the underlying physical and MAX layers. It creates one cohesive end-to-end tunnel, enabling us to guarantee consistent service level agreements, or SLAS, from the source to the destination, regardless of the different network technologies in between. Let's briefly go over the traffic that traverses the network. Two main traffic classes are considered: TSN and best effort. Best effort refers to any traffic that is not marked as priority, such as traffic from other users in the network. The traffic considered time-critical includes the control loop of the robot, its odometry data for the digital twin, and the video feed from the cameras. Before reviewing the results, let's briefly go over our panel to understand what we are seeing. First, we have Wi-Fi latency measurements for best effort and TSN traffic. Ethernet latency is plotted in the same way. 5G latency for TSN flows is shown here, in both uplink and downlink. Finally, the end-to-end latency is shown, alongside end-to-end throughput in both uplink and downlink, and the 5G throughput. What we see first is the network running with only TSN traffic. Take a closer look. A user has joined the system and is generating heavy usage. Let's see how the network responds. We can observe how their best effort traffic is being shaped, and no impact on the critical traffic can be seen. Let's see everything in action. We built TSN, technically a super network,